Welcome again to the NPTEL course on storage systems. In the last class, we were looking at some aspects of redundancy, and then we looked at what RAID1 means, what RAID4 means, RAID5, RAID6, and I briefly went through some of these things and highlighting some aspects. Now, we will get back to the ZFS. Now, as I mentioned earlier, RAID5 has a problem which has been called the write hole by the ZFS designers, and basically I will give some details about exactly what this is. First, it should be clear that if you do RAID in software, the performance is poor. Why is that? You first have to bring the disk blocks to memory, compute the parity and write it back. Okay. Again, the CPU utilization, that is also the fact that you have to traverse the network from the disk all the way to the memory. There could be substantial amount. For example, if it is a storage area network, it might have to go through network controllers, cache controllers, whatnot. Okay. So, but as I mentioned earlier, software RAID is very flexible. You are not limited to exactly one type of disk or whatever. It can be done on slightly all kinds of arbitrary types of storage devices. Okay. So software RAID5 is a bit of a problem. It should be software RAID5. It's not just RAID. If data updated in RAID stripe, you have to update the parity also, because there is an invariant that you are keeping. What is invariant? The invariant is that, like I said in last class, basically the parity is basically the XOR of D0, D all the way to Dn minus 1. This invariant you always have to keep. The parity will always be the invariant of XOR of all these guys. So, if you update the disk, then you have to update the parity also. Then only the invariant is maintained. But our problem is that if the data part updated, but there is a crash or power outage before parity updated, the invariant is lost. Okay. So, we somehow have to make sure that we can avoid this situation. You can certainly not avoid a power outage. This is not something which you have any control over. Nor do you have any control over what is called a crash, a panic, kernel panic. There is no control because this can come in any time. Okay. So, that means that somehow you have to recover from this situation. Okay. So, there are various ways to handle the problem. One way is to say that I will always write full stripes. Whatever I do, I write full stripes. If I do full stripes, that means that even if something happens, I just have to redo it. Okay. If I just redo it, everything will be fine again. Even if I did something halfway, something bad happened, of course, the invariant is no longer true, but if I redo it again one more time, then everything will still be okay, as long as I have the ability to do that. Okay. So, that means that somehow you need to do, some way have to remember what was happening. So, you might have to do some logging, etc. But once you have logging, that means it has to be somehow persistent. There are multiple ways of doing this. Okay. One is you have what is called NVRAM, that is battery backed memory, and essentially you keep track of this information, log it in NVRAM, and then because it is battery backed, in spite of whatever crash or power outage, you may be able to recover from it. So, that is why the reason why people use NVRAM is that it is fast and it is a different technology than disk. So, you will find that correlated failures might be less, and it's expensive, but it is a good solution. That is why NetApp, for example, uses NVRAM and many other companies use it. Okay. So, that is one part. Okay. Other thing is, if you are doing the reason why it is good always to do this full stripe write is that you can do all the writes asynchronously. Okay. and as long as you are able to recover from any problems that occur, you are okay. But the problem with the partial write stripe is that you have to do a read modify write cycle. That means you are going to have to read it first. That means the read latency is very much in the path, in your path. So it's going to be very slow. So the performance is poor. Now because the performance is poor, people like to use something like NVRAM or some logging device to get to write to the essentially do the preliminary write to these devices, and then later those writes will trickle down to the actual read device. Previously we talked about logging in a file system, but now this is logging in a volume manager or at the device level. So basically there are software only workarounds, but this is slow, basically logging. If you use NVRAM, it will not be slow, it can be fast. But if you use another disk for logging, then you are going to be slow. And similarly, a lot of people are now suggesting, instead of using NVRAM, which is costly, why not use Flash? Because it is persistent, probably that might also work. The only problem with Flash is that its write speeds are not that very good compared to a disk. Luckily, it does not have the seek time / rotational latencies. That is where the big win is. The big win for Flash in this game is that you do not have the read and write latency, the rotational and the seek latencies, which can be as much as 15 milliseconds, 10 to 15 milliseconds. So that will essentially limit the logging speed to not more than about 50 to 100 per second, that's all. Whereas if you use something like a Flash, your number of loggings you can do can be a factor of 10 or 100 times more. So as I mentioned, the hardware workaround is for using something like NVRAM, and this can be for both the problems, one for avoiding the RAID performance and the other one for the write hole. What is the write hole? Basically, as I mentioned yesterday, you have there is a failure of one disk. That means the disk is not responding at all. You are timing out. You ask for you are trying to write, and the guy is just coming back and not giving any response, saying just finish writing it. So you know that because there is no response back, you know that something has gone bad. So you want to fix it. So you want to fix it, you have to first reconstruct that particular stripe or reconstruct that disk. That means you have to read all the other disks so that you can copy it onto a spare disk. But while you are reading it, you have to do whole reads of the other disks. And there is always a phenomenon in disks that if you read, there is no guarantee that you will get, let us say, correct results always. There is always some residual, what is called uncorrectable errors. For example, there is something called in disks, you have an uncorrectable error of 1 bit per 10 to the power 15 bits rate. Memory also has got similar, even if you use ECC, you have some similar numbers. So because of this, when a disk dies and you want to reconstruct it so that on a different spare disk, during the reconstruction it can also fail, and that is basically the write hole. So to avoid the write hole, basically you have to again do logging. So basically you can combine both these two things. Avoiding write hole, it means you use a log, and improving the RAID performance also can be a log. As long as the logging device is fast, it will work out well. So the only issue has been that the best logging device for this kind of issues has been NVRAM, which has been expensive. It requires a battery backed memory, which is also expensive. So what ZFS wanted to do was to see if there is a way to avoid this problem. So they came with some model called RAID-Z. And what these guys do is they do what is called dynamic striking, because this design is an integrated design. That means it has got both the file system and the volume manager. The design has been done together. It is not done by two different parties. For example, in Linux, the file system is designed by one guy, the MD or whatever volume manager is there is done by somebody else. Same thing in Veritas file system / Veritas volume manager, though from the same company, they are done by two different teams. So it's not This it's not an integrated design. The ZFS on the other hand has been designed to be in an integrated design. So basically what you do is, what is the problem with writes? The thing is, you might want to do partial writes. That means that instead of, suppose you have a RAID device, it has got 5 disks, of which 4 are data devices and 1 is a parity. Let's say one disk is used for parity. Of course, the parity is going to be spread across all the disks, but for the time being, let's assume that the stripes, for example, 4 disks will have the stripes and 1 disk will have parity, right? Now, if you are going to do any partial write, that means you are only going to write, let's say 64 kilobyte, where the stripe size is only 32 kilobytes. That means it cannot be a full stripe write. A full stripe write will be 32 into 4, that will be 128 kilobytes, right? You are not doing 128 kilobytes, you are writing only 64 kilobytes. So since you are writing 64 kilobytes, you have to update the parity also, right? The only way to update the parity is to read everything and then change the whatever has been changed and write it back, right? So there is a read modify write cycle there, okay? So again, as we discussed before, the read modify write cycle essentially can create a situation where the invariant may not be upheld in case there is a crash or whatever. So what these guys did, the ZFS people did, is why not make every write somehow a full stripe write, everything somehow. Now how can that be done? You have 128 actually 4 disks are there. In principle, it has to be 128 kilobyte stripe and with progressive parity, right? So what these guys decided is, whatever it is, since we have file system information, if somebody writes 64 kilobyte, well, we'll call it mirroring. If it is 128 kilobyte, it will be let us say a RAID with 3 disks plus 1 parity. Okay, that means that the whatever size write you write, you make it a corresponding RAID. So if you are writing only 1 stripe, it will be RAID 1. Okay. If you write 2 stripes, for example, if you write 32 kilobytes, you basically make it into a full stripe write with a parity of another 32 kilobyte. That is 2 64 kilobyte write, you make it into a 64 kilobyte write plus 1 parity. Okay. So whatever writes you write, it's always a full write. You keep on varying the geometry of the RAID device that you are thinking about, and this information is known to the file system. The file system knows at this point in time, because it's integrated design, I am writing 64 kilobytes, therefore I know that it's not a really the full stripe write as would be done by a regular write. Because it knows it's not a real full 128 kilobyte write, it will say that okay, for this particular write, it will be a 2 stripe RAID plus 1 parity. Again, this has become a full write now. Okay. So that's why what they have done is they have systematically made that every write is a full stripe write. Okay. Yeah, under RAID's definition of a full stripe. Okay. So this essentially avoids the write hole, because even if something bad happens, right, you just have to redo it, that's all. You don't have to do anything more. Okay. You don't have to worry about losing the invariant. Okay. So that's why that's called dynamic striping. Okay. It's not fixed stripes. Crawl to maximize throughput as additional. Other thing is that you also, as devices are added to the system, you can also take care of. For example, you had a 5 disk system, 1 new disk is added. Now you don't have to worry about reconverting your RAID 5 on a 5 disk system to a 6 disk system. You can dynamically now have new stripes of with 5 disks and 1 parity. Okay. So when one thing also goes away, you can also try to readjust it in the future. Of course, you might have to work around how to recover from what has been lost, but in the new ones, if you don't have to, let's say, you can start using the reduced size of the set of disks that you need for a full stripe. That also can. So that because information is kept in the file system. Okay. The file system knows all about these things. So when you have to traverse the things, you go from the file system and traverse it. Okay. Whereas if it was not at the level of the file system, then you would not know what is there. Okay. There is no way to figure out where that information has to be kept. Okay. Basically about the fact that there is this particular 2 pieces of data actually are RAID 5 with 2 stripe units plus a parity. Okay. All that information will be scattered all over the place. Nobody has that information, and it's only known to the file system. Okay. So that's not known, and so when you have to recover from the bad situation, it is not possible. Okay. Whereas with the file system keeping the information, you can do it. Okay. So when you read from a RAID C block, for example, also ZFS compares it against its checksum. If there is no match, ZFS reads parity and does community reconstruction to figure out which disk returned bad data. How does it happen? Again, it turns out that there is somewhat what's called a Merkle tree kept. What is Merkle tree? Basically, I have a checksum of some leaves of some structure, and then the checksum of the second level tree is computed to get the checksum of the next higher level. So you basically keep a tree of checksums. So if any time there is a problem, you have to search through the trees, see which checksum actually is bad. Okay. You might have a top level thing wrong, then you have to keep going down and then try on both sides of the trees which checksum actually is not correct, and then keep going down that path where it is not right till you get to the place where actually the checksum is wrong. Okay. So essentially you go down the path which has got the try to locate the place where the checksum has gone bad. Okay. So that is for read. For write, what you do is, as I mentioned, this one never really does any overwriting of data. Okay. You always write to a new location and then atomically overwrite the pointer to old data. That's why snapshots and other things are trivial here. So as I mentioned already, variable stripe size, so that every write is a non-RNA. You don't have to do read modify write. So that means that your RAID, the performance problem is gone now. Okay. So that way, the only problem of course is that you are getting variable RAID geometries for the same application. So the good thing about it is that you might have asked for RAID 5 type of reliability, but sometimes you are getting RAID 1 type of reliability. Okay. It's perfectly fine. Okay. It's not a serious problem, except that your disk utilization will be not as good if you were to have done systematically RAID 5 everywhere, right? So there are some minor problems, but they say that this avoids lots of the headaches that are there in other systems. Okay. Just a minute. So as I mentioned already, when you have to do reconstruction, traverse file system metadata to determine the RAID C geometry. Okay. So again, you start from the like FSCK, right? Here also you start from the top of the file system hierarchy, and every single thing you know, the file system knows what type of RAID geometry it has used for it. Every single block or whatever, right? Or extent, it knows what it is. So using that, it actually goes and traverses those structures in turn. At every level, it knows what the thing is. Right? Yeah. Again, when the file system is not full, it will only have to traverse a small amount. When it is really full, you have to traverse the whole thing. It's just like FSCK also, not any different from it. Okay. Okay. But one interesting thing is that this is somewhat different from a strict volume manager design. In a strict volume manager design, what happens? You have no idea about what is useful information, what is not useful information, because there is no metadata corresponding to data. So you actually have to do a block by block comparison. Okay. And it turns out that the way it is done also is by using something called a dirty region logging. In a traditional volume manager, like for example the Veritas volume manager and other kinds of designs, similar designs, you need to keep something called a dirty region logging. That means when you are writing to for example a mirror, for example, right? It's possible that you could have written on one, and then before you finished it, you couldn't complete the other one, and then you have to resynchronize the mirrors. Now, if you don't have any information, then you have to compare both of them, right, and somehow figure out which is the more recent version, right, and then use that as the new copy, right, and overwrite the old copy. But that means that you have to go through the whole disk, the full virtual disk VDEV, you have to go through. Whereas if you use what is called dirty region logging, you keep a small little another small area in the disk where you note down, just like logging, you note down which sets of logical block addresses are getting written and they have not been written on the other side. Okay? You have to keep noting all those things. Just like logging, you also have to note somewhere. So in some power crash, whatever happens, then look at this dirty region logging and they are able to figure out that only this part has changed, not everything. So if you don't have a design that, so basically unless you use dirty region logging, you have the same, you have a serious problem with regular volume managers. You have to really essentially look at the whole disk. Okay, it can be very slow. Okay. So whereas in this kind of situation, it's only expensive when the pool is full. If it is the file system is not highly populated, then you just do whatever is required. Okay, that's one good thing about this kind of design. Okay. So also while you're traversing the metadata, you can keep on essentially you can use it, the checksum. You can keep on checking the checksum as you go along. Okay. So again, standard RAID, all you can do is to check the XOR invariant. That's all you can do. Nothing more can be done. Okay. Whereas here you can also do the checksum, because the checksum is kept separately from the actual data, right? So that's available at the file system level. So you can keep on checking as you go on. Okay. Whereas volume managers typically they don't have this kind of simplicity of doing it. Okay. If they have to do it. Okay. So basically, in some sense, if you summarize, ZFS RAID differs from standard RAID, how reconstructs only live data. Okay, you don't have to look at the whole disk, because there's no information at the volume manager level, which is a blank or garbage block. Right? Because it's a raw device, there's no information about that this block is being used also. Nobody knows it. That's the definition of block device. The block device in the sense that you just get raw blocks, and you have no idea whether it's being used or not. Only the upper layer knows it. So when something bad happens, you have to copy the whole thing, even if they are absolutely garbage. Which if you had some higher level information, you know that it's garbage, there's no need to copy anything. Okay. So another thing about this kind of model is that you don't need any special hardware. Okay. No NVRAM for correctness, no write buffering for good performance. Okay. You don't need any of these things. Okay. So I think we already discussed there are plus sides of this RAID Z. There are negative, small, minor negative things. So, and because there is checksumming also going on, so it's a reasonably well integrated system for getting good performance as well as avoiding some correctness problems. Now let's quickly look at another design. Okay. NetApp has got some, one of the few people who use RAID4 is NetApp. Okay. There are a few other people who use it, but they are very special applications, but this is a more systematic use. Okay. Now, one of the problems about RAID5, okay, is that if the parity is on different disks, because it's rotated. Because rotated, what happens is that when you are doing data reads, you have to skip over parity disks also, parity blocks also. That means you have to seek past it. So there is going to be some loss of performance because of that. So basically, what happens in RAID5? There are a lot of data stripes one by one, but suddenly somewhere in between afterwards you will get a parity disk, parity block. Okay. And you have to skip over it. But other guys have data. So basically, in some sense, what will happen is that they will keep on getting missynchronized. Okay. As you are reading through the things, suddenly this guy will face a parity block, and sometime later this guy will face a parity block. So you have to keep on going, stepping across. Okay, so that's one problem. Okay, so also what happens is that in standard RAID 5, if you are using a regular file system and your files are scattered all over the place on the disk, that means when you write anything, for example, you are doing you are updating multiple files, right? Since they are scattered on disk, it may be that the blocks are in different places on the disk, and the corresponding parity areas also different places. That means that every write, the parity disk, for example, has to keep on seeking from one place to another place. It has to just keep on seeking. Okay, so that is a problem with RAID 4. Okay, RAID 5, it may be okay because essentially you have equivalent of 5 disk arms because parity is distributed over the things. But RAID 4, that's why RAID 4 has not been used seriously. But NetApp has discovered a very good use for this. Okay, so again, just to summarize, RAID 4, the problem is that if multiple writes go there, the files are in different places and the parities are also could be different places. That means that the parity disk always has to keep on seeking. So you are limited by the how fast the seeks can happen, okay, the write speed of the RAID 4. RAID 5, you have an advantage that you have 5 disk arms for the parity, so it might be helpful. But the only problem is that when you are doing reads, for example, you have to skip over the parity blocks. Okay, there is a negative part to RAID 5 also. So what NetApp what has done is, because they have this notion of write anywhere. So basically what it means is that whenever they are doing any bunch of writes temporally together, right, then they will all be hitting the same areas close by, okay, very close by areas, and the parity disk also will be, and the parity disk also, the areas will be at close enough. So basically what happens is that there, because the write anywhere aspect, it turns out that the seeks on the RAID 4, what we thought was the problem with the RAID 4 is not there in the case of RAID 4, and that is why they are able to use RAID 4. Okay. So basically you can write data and metadata close together, as it does not do in place update. So in a standard, if you in a standard file system, for example, the data and metadata can be different places, because this basically write anywhere. That means the data can go and write, metadata also can go, they can go very close to, just like in a log structured file system. Okay. So that's why RAID 4 is not a problem for NetApp. Okay, and parity disk may or may need to do no or only small seeks. You don't have to do much. Okay. So you can see that there is a interaction between the upper and lower layers here. Okay, it should be very clear. If you have a certain upper level design, then there are certain interesting things that you can do at the lower level and vice versa. Okay. So in here, for example, in NetApp, you have this write anywhere part of it. That means that you are at a particular place, the disk arm is at a particular place, and the idea is that because everything is, there is no update in place, right, you can select a new block nearby, okay, and there is some mechanism by which you are making these blocks available. There is some, I don't want to go into details, but there is some kind of garbage collection that is going on in the case of NetApp file system, by which there is always some amount of free blocks available wherever the disk arm is present. Okay. There is some mechanism. Okay. That is why you are able to do all this. Okay, so we talked about there are 2 types of redundancy models I mentioned. The one RAID 1, RAID 4, RAID 5, RAID 6. They are systematic codes. That means that they are able to give guarantees saying that any 2 errors we can handle, any 3 errors we can handle, any 1 error we can handle, etc. Okay. Then there is other codes, the non-MDS. Okay. they have varying capability to recover multiple errors. But good thing about this is that they are simpler as no solutions involving Galois fields. Okay, this is slightly simpler. One example is here. For example, there is two data blocks D0 and D1. What you do is you take the parity of D0 and D1, that is this, but here instead of you are mirroring D1 and P2. Okay, so this one is using essentially 2 disks to get the parity. Here you are just taking directly this as mirroring. Okay, so there are multiple ways in which you can do these things. Or for example, I have one more 4 or 5 disks. I can have parity of some of them P1, and then P2 will be parity of some other sets of disks, and I can use whatever seems reasonable to me. Okay, that's possible. Okay, and there are some designs by which you can do this. Okay, now depending on how these parities are let's say computed and which data disks are used for computing the parity, you will have various design possibilities. And for example, if you have a 9 disk 6 parity system, it turns out there is a particular way in which you can join various disks to produce some parities. Okay, there's a, and people have computed this. Okay, so that one has a certain reliability measure. Okay, for example, the best one has this reliability measure. What does it mean? It means that any 3 disk failures it can handle without any problem, because that's what means. For example, this gives you how many ways you can fail when so many errors are there. For example, you fail in 0 number of ways when there is only 1 error. You fail, whole system fails in 0 number of ways if there is 2 errors. This is the way in which 0 ways in which you can fail in case there are 3 errors. Okay, that means that any 3 errors it can handle. But there are 30 configurations in which it can fail if there are 4 errors, 4 disk fail. Okay, similarly, there are 390 ways of doing it, and there are 2. So these things have different types of capabilities here. Okay, the good thing about this is that you don't need. If you remember this part of it, right? Basically, if you want higher tolerance to more than multiple disk failure tolerance, right? In the case of RAID 6, you have to solve this equation. Okay, this equation is, people have done a lot of work on how to make it fast, but still it requires some computational resources. Okay, so if you use this non-MDS, you don't have to do any serious computation, you just have to XOR. Everything is XOR. Okay, so but the problem with that is that you don't get the guarantee that you can handle k number of failures in all situations. Okay, that's not possible. You have variable amount of ability to tolerate failure. Okay, that's basically the problem with non-MDS. Okay, but this looks promising, and some people are doing some work in this area. Okay, okay, now let's move on to a slightly different topic. Again, ZFS also uses Flash, and same thing with even the current other solutions from NetApp, etc. Various important players in the game, they all have Flash as a part of their system. Okay, so let's try to understand what is the issue with Flash and what's happening here. Okay, now so far we have been based on a disk-based technology. Of course, previous to that, tape-based technology, which is also still surviving or even flourishing, because it can store really huge amounts of data. Okay, and there are certain guarantees with respect to tape being available even after multiple decades. Okay, so that part of technology is still going on. So whereas Flash is basically semiconductor technology compared to the other two, which are electromechanical, this one is semiconductor. That means what is good thing about this is that you can now integrate CPU, storage, and memory in the same technology. Okay, similar technology. Of course, if you talk to the serious IC people, they will tell you that CPU technology is different from memory technology from Flash. But in principle, from a semiconductor fabrication point of view, they are the same. Okay, from a to clarify it, you can say from fabrication point of view, they are all the same. Whereas with respect to disk, they are not the same. Okay, there is some completely different thing that happens when you have a disk. Then you have certain, things like motors and whatnot that have to move things around, etc., which is a different technology. Okay. So I think that the ability to use the same type of fabrication is a great advantage. I think it's going to dramatically start changing things in the future. Okay. So nowadays you can go to very fairly highly dense flash based chips. For example, you can get in what's called 19 nanometer technology. This is the feature size. This is the smallest reliably you can mark on the chip. Okay. 19 nanometers. I guess it is 19 nanometers is basically, how much is it? It's 19 to 10 to the power of minus 9 meters. So it is 19 to 10 to the power of minus 7 centimeters. Okay. Minus 7. Okay. That means it's 190 into 10 to the power of minus 8 centimeters. That means 190 angstroms. So this is 190 angstroms. And you might know that one hydrogen atom is half an angstrom. So we are talking about something like 400 atoms. Okay. So we are talking about 400 hydrogen atoms sitting there. Okay. That is the size of the lines you can mark on the chip. Okay. And these are based on that. Okay. And they use something called, so basically people are able to make 19 nanometer 8 GB flash chips, and there are various types of flash designs, something called single level cell and multiple multiple level cells, MLC. And single level cells are of course the more reliable because there is only 2 levels, 0 and 1 equivalent of that. Okay. Whereas with 2 bits per cell, there are 4 levels, 0, 0, 0, 1, 1, 0, 1, 1 in terms of some analog quantity. Okay. You have to mark out the analog quantities, okay, from 0 to 0, 0 to 0, 1, 0 to 0, 3. Okay. So this MLC is cheaper, but it has more errors. So you need a good amount of error coding for it. Okay. So Reed-Solomon coding or other types of coding also being used. For example, you might have some XORs, some parities, horizontal, some parities, vertical, all kind of things people are designing. Okay. You can have RAID also on top of these things. So many designs are coming out. One thing about this also is that it has a potential of being lower power. Okay. It's still not the case that it's really low power. For example, I recently looked at one new design from Intel. They say that for a 800 GB kind of device, the amount of power they consume is about 20 or 30 watts, okay, which is again very close to what a disk also does. Okay. So the only good thing about it is that it probably currently it is still not really low power. Of course, this is what is called an enterprise flash, basically a PCIe flash, the number I mentioned just now. Okay. You might have slightly cheaper versions which are really low power, but for these ones it's not really low power yet. Okay. So they are still comparable to disk only in terms of power. But a good thing about this is that if you are interested in designing system which have a certain transactional throughput, then these kind of systems will give you higher transactional throughput compared to disk based systems. So what you would have to do for a disk based system is to have larger number of disks, and that will actually eat up the power. Okay. Whereas here you can work with smaller number of devices, and so that way you are going, because each of them has got a very high transactional throughput rate. Therefore, your power could be lower than if you were to have a comparable system with disk with the same transactional throughput. Okay. Okay. So now this flash has an interesting thing that it has got, in addition to read and write sizes like a disk, it has got something called erase. Basically, once written, you have to erase it before you can write again. And so there is some specific sizes at which you can do this. For example, in many systems, more recent systems, read can be at 4K level, write can be at 16 or 32K level. Arrays can be let us say 256 kilobytes, whatnot, similarly. Okay. So, or it could be, yeah, it's 256 or 512 kilobytes, those kind of ranges. Now, in a sense, what's happening is that you are able, because you cannot write in place, because you have to erase it before you can reuse it. It sort of makes you think that you can do copy and write at the device level. Basically, what you have to do is, you want to rewrite, you don't write the same place, you write some other place, and you change your pointers, right? Otherwise, you're going to suffer a read modify write cycle. Suppose I want to, if I want to update a particular location, the only way I can do it in this particular technology is to read the whole thing, update the portion, and write back again the same place. I have to erase it, sorry. I have to erase it first and then write back at the same place. And the erase size is usually much bigger than the write size. So, what we have is essentially a read modify write cycle. Okay. So, if you want to avoid this read modify write cycle, you might want to think of using copy and write, but these are happening at the device level. So far, we have talked about it happening at the file system level. So, so the question would be, can we use this kind of model efficiently for designing large scale storage systems? Now, one other aspect about the system is that in addition to having to erase before you can rewrite, it has got some wear and endurance. That means that it can be written only so many number of times. Okay. For example, with SLC kind of system, single level cell, SLC, right? It turns out that you can only write about 100,000 times typically. Okay. And then with MLC, you can write about 10,000 times. So, the manufacturers typically make it better than this by using some error codings. Okay. They try to add some redundancy at various places, so that finally the device on hand what you get is, they say that you can rewrite it about, let us say, not exact 100,000 in the case of SLC, but maybe closer to 1 million times. Okay. That is an additional level of let us say organization has to be introduced, so that you can get to that level. Okay. So, yeah. So, that is why you need some newer reliability models. Again, because certain parts of the data can be heavily used and certain parts may not be heavily used, over a period of time different parts of the device will get written at different number of times. That means that the wear level across the device will be non-uniform. So, you have to figure out a way of making sure that if one of them gets overrun too much, then probably you may not be able to use the device. So, you have to figure out a way in which you can wear level the thing uniformly across all the parts of the disk, all the parts of the device. So, there are multiple methods of doing it. There is dynamic models and static models. The names are peculiar, but basically dynamic is what I mentioned just now. Basically, you keep on writing to a new place, and then you do some kind of garbage collection afterwards. Okay. That is, it's determined by writes. Okay. As writes come in, you keep on putting it some other place. Whereas static wear leveling, as it is called, you basically look at the distribution of how many, basically independent of writes, you actually try to move things around. Basically, you do write live data to some other place, and then release those things what has been already written out to some other places. And so, the issue about this is that anytime you do any wear leveling, you are also introducing new writes. So, there is something what is called write amplification that goes on. That is, for every write, possibly some other writes will come in the picture later, because you want to do the leveling. So, this write amplification is an issue. You want to make sure that this does not become big. So, Flash has got some interesting new issues that have to be resolved. You have to do wear leveling and also garbage collection. Okay. Basically, these two things have to be part of your system somewhere, and that's the difference between raw and SSD. Raw systems don't do any of these things for you, you have to do it yourself. This solid state devices, SSDs, solid state devices, they basically have some policy how to do it, and it is internally done in the device, and you may or you may not have complete access to how they do it, but it is done for you, and this SSD essentially gives you the same interface like a disk. Okay. Basically a disk has got for example a SCSI kind of interface, and they will give you a SCSI interface. Okay. Now enterprise flash also is becoming quite common. Basically enterprise flash is what? Basically the same, similar to this flash, but used in high performance or critical information technology systems. Okay. So this as a point of comparison, the number of I/O operations you can do per disk is approximately at the most 50 per second. Okay. Whereas with flash we can get about from 2000 to 8000 okay, per SSD, and this is on 8K random read and write. And if you instead of we also have a variety called PCIe flash, where it is directly sitting on the PCIe bus, for example. You can have even much higher ones. Okay. For example, instead of 2000 IOPS, we can go to probably 38,000 for writes. This 8K is for reads, that is the corresponding here is 90,000. So you can go an order of 10 times or more if you go for PCIe flash. Okay. So of course more expensive, but this is more the high performance kind of systems. Okay. Now just let's just look at a few more things corresponding to this. Okay. Now that a flash has come in, enterprise flash available, do you want to build a file system on top of it? Okay. Now either I am using the flash through SSDs. Now let's just look at, because the SSD is basically giving a disk interface, so essentially there is no major thing here, but it turns out there are still some issues here also. What is one issue? The issue is that if the file system deallocates a block, it is useless, right? But this information is not known to the lower layer. Okay. From the lower layer's point of view, it is still a block. Okay. So it will not be garbage collected, it will not be, it will install, the lower layer still thinks that it is something useful. Okay. Because nobody told it anything, because it's just that from a file system point of view, it moved it from the linked list with respect to a file, it just moved it to the free list, that particular block, right, which was released when it was deallocated. But how does the lower level know that this is something called a free list and there is something called a file list of blocks? It has no information about those things, so it can't figure it out. Okay. So there is a new command that has come in called the trim command. So if you are writing a file system that is going to be mostly on flash, then it may be good for your file system to issue trim commands to the SCSI layer. So this trim is basically a command for a new command for SCSI. Okay. So if a SCSI controller gets trim command, it checks whether it's a flash device. If it is flash device, it actually tells the thing that this particular block is also garbage. You don't have to keep it intact and worry about copying it, because you're doing your own wear leveling, or you're moving around things using static wear leveling, for example. You don't have to try to copy it around. It's basically junk. You just can, without copying, you can move it. You can reassign it wherever you want to do. So trim command is now part of SCSI, set of commands. Okay. So this is in case you use SSDs. What about if you use file system on let's say raw flash? Okay. That means that somebody has to manage where and also the parallelism. I will come to parallelism soon. So basically this software layer which does management is called flash layer translation, FTL. Oh, I issued a flash translation layer. I'm sorry, I got it slightly mixed up here. Flash translation layer, FTL. Okay. And also typically you will find that most of these systems have a write buffer to absorb random writes. Okay. If you are doing it on raw flash, typically there is some write buffer, so that you don't have to, you collect all of those random writes into a pool and then try to send it to the flash. So there is some support. I'll just briefly mention the kind of things that are there in Linux. There is in Linux, there is typically you have what is called the block devices and character devices. Linux has a special type of device called MTT device, and basically it's the way it has been designed in Linux, it's a 512 byte block device. But the problem is that anytime you write to a, because it's a 512 block device, anytime you write to a 512 sector or whatever you might call it, it doesn't let us read, modify, write. So it's pretty awful. It's only useful for typically for read-only file systems. Okay. So there is also one type of FTL, NFTL. Basically, they have what is called primary blocks and replacement blocks. And anytime you do a rewrite of a particular block, you basically keep it in this, you write it into replacement blocks. So in a sense, you have a primary block and its updates, and there's some kind of a chain is kept. So the primary block is the original value, and then you have its own updates. So there will be a chain of these updated values, and once it crosses a certain number of the size of that chain, it goes beyond some amount, some garbage collection comes in and then cleans out all those things again. Okay. So something simple like that has been done in FTL. In DFTL, basically you will notice that for doing this copy and write or essentially non-update in place, you have to keep changing the pointers. So if you have a large flash device, if you assume 512 block devices, it turns out the memory required for keeping these pointers is substantial. It can be close to gigabytes. So that's why most people keep it in the flash itself. That's why you have to go through the linked list of replacement blocks to be able to do garbage collection. You actually have to go through all those things. Where DFTL, what it does is it has decided that I won't put 1 gigabyte, I'll put only a smaller amount, 64 megabytes or whatever. I'll store the recent maps in DFTL. Sorry, I'll store the recent maps in SRAM, and rest of it will be as usual in the case of, I'll keep the actual other updates, the full table in the flash itself. Okay. So that's what they have tried. Okay. Now, one thing that people often have noticed is that there seems to be a good fit of flash with log structured file systems. Because what is a log structured file system? You keep on, you have the log itself as the primary way of storing information, and if your array size is, let us say, 512 kilobytes or 1 megabyte, then what will happen is that you can buffer all the writes in memory as a log, and then every so often you push out these 1 megabyte segments or 2 megabyte segments or 512 kilobyte segments and write it full in one shot to the flash in its array size units. Okay. If you do that, then essentially you are exploiting the flash for its capabilities. So that's why there is a file system on Linux called YAFFS2, and this is basically a log structured file system. But a log structured file system has a need for garbage collection, because once you have you keep on accumulating the writes in a segment, fine, but the thing is that you might be doing overwrites. That means that you might have written a value v1, and then just moments later you would have got a value v2 for the same block, and the value v1, that block, because you are not doing it in place, is now garbage that has to be reclaimed. So that means you have to do some garbage collection. Okay. So log structured file systems do have to do garbage collection, so that if you do multiple rewrites, you only want to keep the most recent write, and the other previous writes have to be sometime be reclaimed, right. So, so the garbage collection overhead is very much there for this kind of systems, and but there seems to be a good fit of a log structure file system with Flash. So, this kind of file systems are also quite common. So, I think I will briefly touch upon parallelism and then I will conclude today. Okay. Basically, it turns out that there is a lot of parallelism in the these kind of devices. If you look at a disk, there is only one single arm, that limits the parallelism, whereas here what happens is, because the semiconductor technology, you will have lots of possibilities. If you are aware of the DDR RAM memory, for example, it comes with multiple channels. Okay. So, here also this is multiple channels, and so that means that each channel can be, you can pipeline it across these channels, you can do lots of things of this kind. Okay. And so, basically this is multiple channels, each channel is multiple flash packages, each flash package is multiple flash chips, each flash chip is multiple dies, one die has got multiple planes. So, so many levels of parallelism is there. Okay. So, you can get as much as 64x or even higher levels of parallelism in these kind of systems, and the issue is how do we expose it. And there are some problems here, and for example, standard Linux IO queuing is not suitable, because it turns out that for a disk the kind of time sitting in the IO queues is not a problem, but with Flash you are talking about some tens of microseconds for write. The same amount of queuing will actually kill the performance of the device. So, you need to actually have a different system, because in Linux what happens is that they do a lot of what is called accumulating all the writes in a particular way. Okay. Something called plug-in architecture is there, plugging or something they call it. So, those kind of things are not suitable. Okay. So, you have to develop a new model altogether, and there is a difference in read and write sizes, and there is, because you are doing it at a much faster rate, you may want to think of using polling rather than interrupts. Okay. You also have to schedule read, write and erase, okay, and also the garbage collection and prefetch. You have to think about how to do it systematically. There are a lot of parallelism, but you have to also schedule them. Okay. Another interesting thing about this is that now that you have so much higher IOPS, previously the storage system could have been a bottleneck, but now other part of the system also could be bottlenecks. So, that you have to again re-engineer the system so that it is reasonable design. So, I just summarized now. Basically, if you are thinking about file system design, there are many issues to be thought about. First of all, we have multiple types of clients, right, starting from user level programs, then management applications and whatnot. One important thing we have to do is to bridge memory and disk speeds. There is a lot of, you need to actually somehow exploit the concurrency levels. Newer technologies are showing up, and there might even be new security issues, because now things are persistent. So, you may want to see how to prevent some information to be permanently be there when it should not be. Okay. So, there are reliability issues, and how do you integrate the volume manager with the file system, those kind of issues, or like Google file system has done it, drop all these ideas about RAID and then do error coding across by having copies across multiple systems. Okay. So, those kind of designs are possible. Okay. So, the design space is quite large and something that has to be systematically looked into. Okay. So, I will stop here at this point.